It's great to come your way once again. In our previous lesson, we have looked at how we can decompose rational functions into partial fractions, and we have looked at examples on the linear factors. My name is Nana Awedu, and you can call me Say Nana. Remember to like this video, share this video, subscribe to my YouTube channel, and don't forget to click on the notification bell so that you can get all videos on time. In this lesson, we want to look at another way of decomposing rational functions into partial fractions. We want to consider when we have repeated factors and what it means, or how we can decompose repeated factors of rational functions into partial fractions. Now let's consider repeated factors. So for rational expressions with repeated factors, right, as denominators, we can decompose it, right, when we have a rational expression of this form. So we see a repeated factor in it, for example, x minus p all cubed. This implies that, for instance, we can have x minus 1 all cubed. And that would mean that the factors are x minus 1, right? X minus 1, and then x minus 1, right? So it means that it has three factors which are all x to be equal to 1, right? So all the three factors are x equal to 1. So in that case, what we must do is that we write a all over x minus p. In this case, x minus p all cubed. So all over x minus p. Then plus b. The next one, we go to x minus p all squared. So it's like we are climbing, right? Then plus sc s minus p all cubed. So let's assume that it was probably something like ax plus b all over x minus a all squared. Then it means that in that case, you must have our a x minus small a plus b, right, x minus a all squared, right? So we end at the square, right? Where we get to the square, then we end. In this case, it's cube, so we go s minus p all squared, then x minus p all cubed, right? So let's consider an example so that this looks clearer for us. So the example is asking us to resolve x plus 3 all over x plus 3 all squared in partial fractions. So we want to go by the means of partial fractions to resolve this, right? So let's look at how we can resolve this in partial fractions. So we have been given an expression x plus 3, right? So we have x plus 3 all over x plus 3 all squared. So since this is a repeated factor, we can write it as x plus 3 all over x plus 3 all squared to be equal to a all over x plus 3, then plus b all over x plus 3 all squared, right? So we go through the same procedure. We write the left hand side again, so x plus 3 all over x plus 3 all squared. Then we find the LCM on the right hand side. Now we see that the LCM of x plus 3 and then x plus 3 all squared will be x plus 3 all squared, because x plus 3 can go into x plus 3 all squared, right? So when x plus 3 goes into x plus 3 all squared, we have a multiplying x plus 3, then plus b, right? X plus 3 going to x plus 3, that will be 1. So 1 multiplied by b will be b, right? So we see that since the denominators, right, the denominators are the same, then we can equate the numerators and have 12, in this case is x plus 3, to be equal to a multiplying x plus 3 plus b, right? So let's expand and form our simultaneous equations and use that to simplify. So we have x plus 3 to be equal to a multiplying x to be ax plus a multiplying 3 will be 3a plus b, right? So in this case, we want to compare coefficients. So comparing coefficients, we can see that right, our x, the coefficient of the x is 1, right? So the number by the x here we know is 1. So you can write that 1 is equal to, here our x is only 1 and then the coefficient of it is a. So 1 is equal to a. You can call that equation 1. Now constant 3 here. So 3 is equal to all the constants here, which is 3a plus what? B. So we can put a, which is equal to 1, into, let's call this equation 2. Equation 2. So that implies that we will have 3 is equal to 3 multiplying 1 plus b. So we have 3 is equal to 3 plus b. So it means that b becomes equal to 3 minus 3. Right? So it means that b is equal to 0. So therefore, we can write our x plus 3 all over x plus 3 all squared to be equal to, right, our a is 1. So we have 1 all over what? S plus 3. Once the b is 0, it means that the b part goes to 0. And this is entirely true because even without the use of partial fractions, when we consider the expression given, which is s plus 3, right, all over s plus 3 all squared, we can cancel out. And it means that will give us what? 1 over what? S plus 3. But please, when you are asked to resolve using the partial fraction system, you can't do it this way. This one, we are only simplifying. You see, once we simplify, we are getting the same thing we have here, right? So basically, in this lesson, we have looked at how we can resolve partial fractions, right, or rational functions into partial fractions. And we've considered when we have repeated factors, what we must do. We have used an example to be able to solve, right, the repeated factor, and we've been able to get, right, our partial fractions resolved. In our next lesson, we want to consider another example on how we can solve partial fractions using the repeated factors. Remember to like this video, share this video, and subscribe to my YouTube channel. See you in the next lesson.